Good morning, children, once again. So in continuation with what we were doing in physics, I have brought you another video and if you remember the last time we were doing something related to equilibrium, and I had told you that there are two types of equilibriums. Equilibrium is basically a state of stability. Now there are two types: static equilibrium, as you can see over here, and dynamic equilibrium. Static, this is the explanation. Dynamic, this is the explanation. I'll read it out for you. Please follow. Body is originally at rest. Body continues to be in rest even after the application of forces. Please note the word is forces. So there are multiple forces that will act on the body. The body will be initially in rest. So you can follow it up with this diagram over here that I have drawn as an example. This is a surface, a flat surface on which there is a body that is kept, and in brackets I have written the body is in rest. So afterwards what happens is, you see, body still in rest even after the application of these two forces. Now as you can see, this force has a magnitude F and it is in that direction, and this force also has a magnitude F but it is acting in the opposite direction on the body. So obviously what is going to happen is these two forces are going to get neutralized, thereby creating no effect in the state of the body. So body was initially at rest position, body will continue to be in the rest position. This is what is known as the static equilibrium. Static is not moving, stationary. Okay, so this is what is known as static equilibrium. Now moving on to, so where do you exactly see this static equilibrium? Is in cases of beam balance, where you have both the pans balancing each other. Okay, so now we come to dynamic equilibrium. Dynamic, as the word suggests, dynamic means something that is in motion. Okay, so body is originally in motion, okay, and body continues to be in motion uniformly even after the application of forces. Okay, so the basic difference between this and this type of equilibrium is that this body will be in rest, this body will be in motion. Now you see, the example will give you a better view of what this is. I have taken the example, the book also mentions this example, you can have a look later in the book. Raindrops falling with uniform speed. Now just take a practical example of raindrops falling from the sky. The general perception that everyone would have is that the raindrops are getting pulled due to the gravitational pull of the earth. They are being pulled downwards and they are in accelerated motion, but that's not the case. Once they start going downwards, initially their motion is accelerated, but then what happens is, here the gravitational pull on the raindrops, which is in the downward direction, is balanced by the buoyancy and viscosity of air. Buoyancy, viscosity, obviously as of now you won't understand, this chapter comes a little later in 11th, 12th standard, but buoyancy you have studied in 9th standard. Buoyancy, anything that is moving downwards in a fluid, the fluid will be exerting an upward force which resists the motion. So basically there are two forces acting. One is pulling the raindrop downward and trying to accelerate the raindrop downward, whereas the buoyancy which is acting upward, the buoyancy because of the air, it is in a way neutralizing that effect. So what happens as a result? Does the raindrop stop in between? No, it continues moving downwards with a constant speed, okay, with a uniform speed. So essentially what has happened in this entire process is, body was originally in motion. Where is the body? Which was the body over here? The raindrop. Okay, so it was in motion earlier and it continues to be in motion uniformly even after the application of a number of forces. Okay, where are the forces here? The buoyant force, the gravitational force, the viscous force. Okay, so all these forces. So static and dynamic equilibrium. Now coming to the conditions for equilibrium. What are the conditions that are necessary for any equilibrium to exist? There are two conditions. The resultant of all the forces acting on a body should be zero. As you can obviously see over here, the resultant of these two forces acting on the body is producing no net result. Therefore, that's one scenario. And second scenario, we have already studied in the previous lecture. Algebraic sum of all moments of forces acting on the body should be zero. Now, moments of forces, this is the word that you have to be careful about. Moments of forces, we have already been studying this for quite a long time now. Moments of force is basically the turning effect that the force creates. Okay, so all the anti-clockwise moments and all the clockwise moments, that is clockwise moments in this direction, anti-clockwise moments in this direction, if they are going to balance each other, neutralize each other, this is what this equal to sign tells you over here. So if all the clockwise moments and all the anti-clockwise moments come out to be equal numerically, then what happens is they neutralize each other and there is a state of equilibrium that is maintained. The second point, as you can see, I have written, this is also called principle of moments as taught in the previous video. So if you go back to the previous video, if you want a clarification, if you have not watched the previous video, please go to the previous video and see principle of moments. What does principle of moments state? It states that in equilibrium, sum of all clockwise moments will be equal to sum of all anti-clockwise moments. So this is what the principle of moments is, and this is what will be applicable in the numericals that we have been solving. So I have brought one more numerical today. We'll solve that just immediately after this. Okay, so I hope this is clear now. Okay, so here's the question that I have taken up. Please read the question properly. A uniform meter rule of mass 100 grams is balanced on a fulcrum at 40 centimeter mark by suspending a mass m at the 20 centimeter mark. Now, you see, you probably won't be able to understand the question if you read everything all together. Let us go step by step. So, the first important point over here is that it's a uniform meter rule. Now, meter rule means, so I'll just draw the meter rule for you. It's a uniform meter rule. As you can see, a uniform meter rule I have drawn over here. So since it's a meter rule, you will have 0 centimeter over here and you will have 100 centimeter. So it's a meter rule. It is 1 meter in length. Okay. The word uniform over here means that the mass is equally and uniformly distributed throughout the ruler. That means the ruler is uniform throughout. It is not thick at one end, it is not thin at the other end, it is uniform. What is important about a ruler being uniform is that its center of gravity falls right in the middle of the ruler. So essentially what is going to happen is, this is what a uniform meter rule is going to be, and at the 50 centimeter mark, which is right in the middle, you will have the weight of the ruler acting right at the midpoint. So that midpoint, if I mark it, it will be like 50 centimeter in between. Now, the next important thing is, where is our fulcrum? Where is our pivot? Okay, so as you can read in the question onwards, a fulcrum at 40 centimeter mark. Okay, so supposing that here you have the 40 centimeter mark, so here you have the fulcrum. Okay, so this is the 40 centimeter mark, and here I have marked the fulcrum or the pivot. So you can mention this as the pivot. This is that fixed point about which the ruler will be balanced. Okay, so the next important thing, again, please read, the ruler is balanced. Okay, so that means it is neither tilting to this side nor tilting to the right hand side. But as of now, please have a careful look at this setup and tell me if you see two forces acting. I don't see two forces acting. I only see one force which is because of the weight of this ruler acting over here. Okay, so this weight of the ruler is obviously going to try to tilt the ruler in a clockwise direction. So you have clockwise direction over here. Now obviously the logical thing is to think that if we are to balance this ruler, then this clockwise movement or the clockwise turning effect should be balanced by another moment which should be in opposite direction. So the other moment should come in this direction and it should be obviously in anti-clockwise direction. So where is that second force that is going to produce this anti-clockwise moment? Please read the question further. By suspending a mass m at the 20 centimeter mark. So supposing that this is the 20 centimeter mark, they are suspending a mass m. Okay, so they are suspending a mass m at the 20 centimeter mark. Now when you see, because of this mass there will be some weight. Okay, so this mass is going to pull the ruler in anti-clockwise direction, and the weight of the ruler which is acting on the right hand side of the pivot, it is going to try to pull the ruler in the clockwise direction. So these are two opposing forces, okay, opposing moments. Okay, so since the ruler is balanced, so what we will do is we will apply the principle of moment. So according to principle of moments, what happens? Sum of all clockwise moments will be equal to sum of all anti-clockwise moments. Okay, so clockwise moments, we are talking about this side of the moment. Okay, so clockwise moments, there is only one clockwise moment, so sum does not really make any difference over here. Clockwise moment, what is the formula for moment? Force multiplied by the perpendicular distance. So which force are we going to take? It is this force that we are going to take, and if you remember, the mass of the ruler is already given in the question as 100 gram. So this is going to be 100 GF. Okay, 100 GF. Why GF? Now you please try to understand this. This is the force that is acting. Okay, the formula says force multiplied by the distance. Okay, and force is nothing but the weight, and weight comes when we multiply m and g. Okay, so now mass here was given as 100 gram, so I am going to use the gravitational unit of force, so 100 GF. Okay, so let us write 100 GF multiplied by, what is the perpendicular distance from the pivot? Please remember always, for moment of force it is force multiplied by the perpendicular distance from the pivot. So pivot is at 40, your force is at 50. So what is this distance? This distance is going to be 10 centimeters. Okay, equal to, now sum of all anti-clockwise moment. There is only one anti-clockwise moment also. So m multiplied by, because this mass you don't know, so I'm going to write it as m. Okay, m grams multiplied by, you have this as the perpendicular distance. So that is like your force is acting at 20 and the pivot is at 40, so this is going to be a distance of 20. Okay, so 20 5 is 100. So your mass becomes 5 into 10, which is going to be 50 grams. Okay, mass is going to be 50 grams. So if you see, they had in the first part they had asked you find the value of m. Okay, so the mass has come out to be 50 gram. It is this mass that we are talking about. Now let's go to the second question. To which side will the rule tilt if m is moved to 10 centimeter mark? Now let's see, before moving into the next situation, let us see what is the current situation over here. Is the ruler balanced? Yes, the ruler is balanced. The question says so. That means when m is at 20 and the weight is at 50, the ruler is horizontal, balanced. Okay, so obviously if you are going to make any changes in the positions of these forces that are acting, then obviously the balance will be no more there. Okay, so the new case that we are going to have is, now I am going to make a new diagram for this second case. Let us make a new diagram over here. Suppose this is your 0 centimeter mark and this is your 40 centimeter mark where we have the pivot. Okay, this is your 100 centimeters. Okay, at 50 you have at the 50 centimeter mark you are having the weight acting. Okay, and this time the mass m is moved to the 10 centimeter mark, so it is being moved to the 10 centimeter mark. Okay, so this is going to act like this. Now for answering the second part, you actually don't need any calculation. It is just the logical understanding. This is the previous situation and this is the new situation. We have not moved W. The thing on the right side is still the same. What we have done is we have moved this mass M, which was acting at 20, further away from the pivot. By moving it further away from the pivot, what has happened is this distance, the distance between this force and this pivot, which was earlier 20, as you can see here in this diagram, this was 20 centimeter. This has now increased to 30 centimeter. This has now increased to 30 centimeter. Okay, so obviously this distance has increased. So what will happen is the ruler is going to tilt in this direction, which is the anti-clockwise direction. Okay, so the answer to the second part will be, to which side will the ruler tilt? If m is moved to the 10 centimeter mark, it is going to be tilted in the anti-clockwise direction, or you can also say on the side on which we have mass m attached. Okay, so that is the case over here. Now we already know the value of m from the calculation over here, so I am now going to write this mass m as 50 grams. Okay, we have already calculated the mass 50 grams over here, so the weight that will be acting here will be 50 gf. Okay, please remember, mass is not taken in this formula. In this formula, force is taken. Okay, so force, that is the weight, will become 50 gf. Again, obviously this is also the gravitational unit. Okay, now so coming to the third part, what is the resultant moment now? Obviously the resultant moment now is not going to be zero, because now after the movement of this mass to the left hand side, there is a tilt to the anti-clockwise direction. So let us find out the overall resultant moment. So once again, anti-clockwise moment we will calculate. Anti-clockwise moment is in this direction. That will be the force, which is 50 gf, multiplied by the distance, the new distance, that is 30. So that makes it 5 3 is a 15, 0 0 gf cm. Please note the unit. This is moment that we are calculating. The formula is force into distance. Force is in gf, distance is in centimeter, therefore moment unit will be gf cm. Okay, and obviously the direction I have already written, anti-clockwise moment. Now the clockwise moment. Clockwise moment, again the formula is force multiplied by the distance. Force this side, which is, as you can see, we did not change W value. W value is still 100 gf. So 100 multiplied by this distance also we did not change. So 40 to 50, the distance is 10. So this is going to be 1000 GF cm. Okay, and now you can obviously see that they are not equal, although they are in opposite directions, but they are not going to be neutralized fully. So the resultant moment is going to be 1500 minus 1000, which is going to be 500 GF cm. What is going to be the direction? The overall direction? Anti-clockwise, because this value is more. So you have anti-clockwise direction of the resultant moment. So it is this resultant moment that we had to calculate. Okay, in the third part, as you can see, what is the resultant moment now? Now means after the shifting of the mass, this is the resultant moment. So this is what is the solution for the third part of your problem. There is a fourth part also to this question. If you people have the book, you can refer to the book and try and solve the fourth part also. That is also pretty simple. Okay, so now the next topic in the same chapter is center of gravity. The short form is capital C dot capital G. Now I have written a few things down just to save time. Let us first go through that. Center of gravity, as we already understand in layman's term, it is a point on or outside a body where the whole weight of a body is apparently acting. Okay, so center of gravity, we say generally for the previous question that we discussed in the same video, for a uniform meter rule, the center of gravity is at the midpoint, at the 50 centimeter mark. Who told us that the center of gravity is at the mid mark? Who told us that? The word uniform meter rule told us that. Uniform, the distribution of mass is uniform throughout the ruler. That is why the overall weight of the ruler is going to act at the center. But do you suppose that all bodies in this world, all practical case scenarios, you will get a uniformly shaped body, a uniformly distributed mass of the body? No. We can have a body, an irregular body like this also that I have drawn. Okay, so we are going to determine how to calculate, how to find out the center of gravity, where will be the center of gravity in such an irregularly shaped body, and how are we going to do that. Okay, so for the beginning, let's just keep this in mind, that center of gravity is a point which can be on a body or outside a body also, where the whole weight of the body is supposed to act. Now, it is also decided by the principle of moment. So how, like for example, in this particular diagram, this point is the center of gravity. How did we come to know that? So we will apply principle of moments to get this point. Okay. Third point, it is a point about which the body is balanced or can be balanced. Okay. So keeping these points in mind, let us now come to this irregularly shaped body. Now, there is a body, let's say for example, let me draw a uniform shaped rectangle. Okay, and this has uniform mass distributed throughout. Okay, so if now somebody asks you, let's suppose that this is a uniformly rectangular shaped cardboard, where is its center of gravity going to be? So you will say right at the center. How do you get that center? You join one diagonal, the other diagonal, the point of intersection is going to be where the entire weight of this cardboard is going to act. So this point is the center of gravity for this particular shape. Okay. Similarly, for a circular shaped body, okay, suppose this is uniformly distributed mass is there in this circular cardboard also. So again, the center of this circle is going to be the center of gravity. How are we able to determine these center of gravities so easily without any calculation in such cases? Because these are known, you can say known shapes, and shapes that we already have an idea about. Okay, and these are uniform shaped shapes that we have. this body, whereas if you have a look at this body, this does not have any particular shape. You can't say that this is a rectangle or a circle or an ellipse. No. So this is an irregular shaped body. This example will be taken to actually go into the details of how to calculate the center of gravity. So this was just for the explanation, a better understanding. Now coming back to our case, the irregular shape. Now suppose that this is the center of gravity of this body. If this is the center of gravity, then all the anti-clockwise moments about this particular point and all the anti-clockwise moments should be matching. All the clockwise and all the anti-clockwise moments about this point should get neutralized. Okay, it is only then that the body will be balanced at this particular point. Okay, so now for that what we are going to do is we are going to assume that this large shaped body is comprised of small masses or small weights distributed throughout the body. Okay, so there will be a mass here, weight here, weight here, weight here, here, number of them. Okay, but since we can't take so many of them, so what I have done is, to the right side of this point I have taken one weight here, one weight here, okay, then one weight here and one weight here. So two weights on the right side, two weights on the left side. Okay, so obviously now the principle of moments has already given us an idea that whatever weights are on the right side of the pivot, they are going to produce a clockwise moment, and all the weights on the left side, they are going to create a anti-clockwise moment. And for equilibrium to be maintained, clockwise and anti-clockwise moment should be equal. That is where the principle of moments comes. Okay, so in equilibrium, what is going to happen is clockwise moments will be equal to anti-clockwise moments. Okay, you can write sum of. Okay, sum of. Okay, so all the clockwise moment. Let us see where are the clockwise moments. W1 multiplied by, what is the formula for moment of force? Force multiplied by the distance. So this is the force acting, and what is its distance from the pivot? This is the line of pivot that is going, the line of you can say the axis of rotation. So D1 is the distance here, so that is the moment because of W1. Similarly, moment because of W2 will be W2 multiplied by its distance, which is going to be D2. Okay, equal to, anti-clockwise moments are because of W3 and W4, so we are going to have W3 multiplied by D3 plus W4 multiplied by D4. Okay, so obviously just for ease of calculation I have taken two weights on the right, two on the left. Obviously there are going to be many more, okay, with their individual distances. So this is the concept that we usually use to find the center of gravity of an irregular shaped body. Obviously all the regular shaped bodies you already know by the geometry of the figure. Let's say for example this is a hollow metallic rod. Okay, so where is its center of gravity going to be? Center of gravity is going to be somewhere in the center over here. Similarly, if you take a hollow circular plate or something like this, the center of gravity is at the center. The reason why I have picked these hollow examples of hollow shapes is because you see, center of gravity is a point which can be on the body or outside of a body as well. So if this is the case of a ring, obviously there is nothing, no matter present over here. The matter is present only over here. Okay, the matter is present only over here. So this is the center of gravity, which is not falling on the body, it is falling in the center of the body. Okay, similarly if this is a hollow cylinder, then center of gravity is over here. There is no mass over here, but the center of gravity is over here. Okay, so that is about the center of gravity. There are some other shapes also given in the book, you may have a look. Now just to test whether you have actually understood the concept of center of gravity, let me pose one question. If the question is, let's say for example, what is the factor on which the factor deciding the position of center of gravity for a body? Okay, so what do you think can be a factor that can decide where the center of gravity will be for a body? Obviously it is going to be the distribution of mass. Distribution of mass and the shape of the body. If the body is irregularly shaped, you will have different positions based on the shape. If you have a regular shaped body, you already know where the point or the center of gravity is. So what is this distribution of mass as a factor? What do you understand by the distribution of mass? So you see, I'll take a basic example just to help you understand. Suppose that there is a meter rule. Okay, suppose that there is a meter rule. This is 0 centimeter mark and this is your 100 centimeter mark, and I say that this is a uniform meter rule. Uniform means that the mass, once again I am explaining, that the mass throughout the wooden portion is uniformly distributed throughout. So in that case the center of gravity is going to fall midway. I have already told you that. So this will be the center of gravity. Okay, so what was the factor that decided that this would be the center of gravity? The uniform distribution of the mass. But suppose I tell you that the uniform mass, the distribution of mass is not uniform. On the right side of the ruler there is more wood. Okay, here on the right side of the ruler, the wooden material is more thick or more densely put into the ruler. In that case the center of gravity is not going to be exactly at the center, obviously, because there is more mass distributed on the right side, so the center of gravity will also shift a little to the right. Okay, so in that case you may have the center of gravity slightly to the right. Okay, so this is where the distribution of mass comes as a factor. Okay, so as long as the mass is distributed uniformly, the center of gravity will be the geometrical center of that body. But if the mass is not uniformly distributed, then center of gravity shifts towards more mass. Okay, so I hope you have understood all what I taught in today's lecture. Next we shall cover up the centripetal and the centrifugal forces and the uniform circular motion.